All right, thank you very much. Thank you very much for the introduction. My name is Mina Chetin-Kaya-Randall, and I do a lot of things. And today what I want to talk about is something I've been working on over the last 2 years with a new role I assumed at Duke, and how that kind of factors into my thinking about teaching data science using R. But I want to start telling the story about teaching this material, some of which is very novel, in a pretty traditional statistics program. So one of the roles I have at Duke is I am the director of undergraduate studies. So that's usually how I go about my day, kind of smirking. And then a student comes about, a first-year student, and says, I'm interested in stats, but I have no idea where to get started. So my hands go up in the air. Yes, this is a good development. And then I start thinking, I don't know what the right answer is. Is the right answer Stat 101? So what I mean by Stat 101 is this is a course that I've taught for many years. I think it's a fantastic course, but it is what we call a service course, meaning that a lot of the students in this class, and this is a large class of 120 students, we run 2 sessions of it per semester. A lot of the students are going to be not continuing on with stats. So this is the only quantitative course they take, and we spend a lot of effort and energy trying to motivate them to learn more. Is this the right environment for a student who says, I want to do stats for the next 4 years of my life and be a statistician or a data scientist and do something amazing with data? I'm not really sure, because they're going to be the minority in the class. Is the answer calculus? That makes me even more upset. And not that there's anything wrong with calculus, and to be honest, I think the answer is you have to take calculus as soon as possible, because if you are going to be a stats major, you're going to need it for your theoretical courses, which has to be part of your curriculum. But to say to a student who's saying, I'm excited about data, to say, go take Calc 1, that just simply does not seem like the right answer. Is the right answer probability theory? So up until now, it had been the case that, at least in my department, and I've looked at many curricula as I've been kind of thinking about what the right way to go about this is, indeed, the first course in a stats major is probability theory. I think this is a fantastic answer for the student who is interested in statistics from a mathematical perspective. This is not true for a majority of the students we see nowadays. Also, a course like probability theory tends to have a lot of students from the math department there as well, and that is not the first math course they're taking. So they've matured in terms of their mathematical preparation. And to put students in there who say they're interested in data but don't yet have the same mathematical preparation, or at least that many years of experience, does not seem like the right answer. An answer that makes our students very happy is go take the regression course. You have potentially taken an AP stats course that's advanced placement, where they get to take what is supposedly a university-level statistics course in high school. Students love this answer because the number for that course starts with 2 as opposed to 1, and that just seems like, well, we've skipped over all the 100-level stuff, and we're in a 200-level course. But that's not really the right answer either, because then it really makes the audience in that class very diverse. Those who have gone through some stats, those who have seen some R, versus those who have not. And to be teaching them advanced regression models, but having to constantly backtrack and remind them some of the elementary stuff in terms of both stats and computation, makes it really difficult to teach that course efficiently. So I think this is where I landed finally. We need to change how we get our students started with statistics and insert data science right in there, because that is an opportunity to add computation early, and that can be a course that students can take concurrently with other mathematical preparation courses that they need to take. This sequencing thing is an important thing if you think about college, because we only have the students for 4 years. In fact, with a lot of financial constraints that students are working with, increasingly we have our students for about 3.5 years, and they try to just take as many courses as possible as early as possible, so that maybe they can skip out on paying for that last semester. So trying to sequence things in a way where they get to exciting stuff early, but still are able to take the other core courses they need to take, is an important consideration in curriculum design. So what I'm going to talk about today is the motivation for this course. I'm going to talk a little bit about the syllabus. The computational aspect of it is what I'm going to focus more on and think about how do we introduce R the right way to this crowd of new budding data scientists. I'm also going to give some data analysis examples, but I'd like you guys to be kind because the data analysis examples I'm going to be giving are indeed from my students' submissions that I have gotten the permission to put up here. So at some points, we're looking at code written by people who have been using R for maybe 3 to 4 weeks in their lives, okay? We're also going to be talking about interest and impact, and finally conclude with some further curricular considerations of where does this material fit in. So let's start with the motivation. The goal is to have a course that provides a gateway experience to students wanting to get started with statistics, and that is modern. I think this is important that we teach our students modern tools. These are the students who, at the same time as taking our courses, are looking at, fantastically cool data visualizations on New York Times. So if we are to teach them stuff where what they're producing looks so far from those pictures, it's hard to get them excited. That places data front and center, meaning that our problems that we bring to the class are driven by data examples that they care about. That is quantitative, absolutely. This is a statistics course after all, but it's not necessarily mathematical and does not require additional college-level mathematical preparation. That is different than high school statistics because we don't want to be teaching a course where they could be doing everything with a TI calculator. If you know what I mean by that, you know the pain. And we want the course to be challenging, obviously, but we don't want the course to be intimidating because it's intimidating gateway courses that have been shown over and over again in education research that actually contributes to lower levels of diversity in quantitative and STEM fields. So hopefully, in addition to all the ambitious goals a course like this has, it can also speak a little bit to increasing diversity in the field as well. So this course should emphasize modern and multivariate exploratory data analysis and data visualization. Pictures get people interested. Pictures that tell meaningful stories get people interested. Histograms, I don't know. They don't always get people interested. So we want to make sure that we are looking at multivariate relationships that tell interesting stories. We want to teach, not just expect, but actually teach reproducible computation. This means that time needs to be carved out of your class to teach the tools to do reproducible computation well, and perhaps that means something needs to go from your traditional IntroStat class. We want to start at the beginning of the data analysis cycle with data collection and cleaning, giving students just nice rectangular data sets that they can perhaps even view in one screen. Perhaps those toy examples are useful for building concepts up, but they don't go too far. We want to approach statistics from a model-based perspective. So this is a course that also needs to prepare students for a second course in statistics, which is going to start with building regression models. So there are certain statistical concepts and certain probability concepts that they need to learn, but I don't think they need to learn how to hand calculate every other type of standard error for doing every other type of hypothesis tests. If we can frame our questions in terms of models, we can still prepare students for that course, and with the time we earn from going down that rabbit hole of reciting formulas over and over, maybe we can bring in some of the other stuff that I've been talking about. We want to encourage and enforce working collaboratively, and when I say working collaboratively, I don't mean why don't you slap on a group project at the end of your class? Students hate this, and they do so with reason, because the end of the class is when finals is. It's when they're stressed and when they want to just go home and take a break. That's not the time to meet people to work with that your grade is going to count on. So we want to make sure that this carries out throughout the class so that we can actually convey to the students that, no, this working relationship is going to be part of your life once you graduate from here as well. So they need to think, code, write, and present collaboratively throughout the semester. And we want to underscore effective communication of findings. Telling stories with data does not just end at building pretty pictures. You want to also make sure that you have a good narrative to go along with it. So we want to make sure that we are spending the time to focus on the communication of findings, as well as the steps that bring you to the findings themselves. But maybe more importantly, we want to ask questions that students want to answer. Let me tell you, I think very few students know what an urn is, and they're not really interested in drawing marbles from an urn and then calculating probabilities from that. So let's ask questions that they want to answer. And I don't think this means dumbing anything down. Our students are interested in interesting questions. They want to look at current survey data to find out about what people are thinking about, say, marriage equality. So bring that into the class. So thinking about questions that students want to answer doesn't mean everything has to be fun. Things can stay very serious and impactful. And we want to also equip these students with the tools to answer questions of their own choosing. That means that give them the right tools, such that at the end of the semester, you can tell them, great, you have your toolkit now. Go find a data set you're interested in and analyze it with everything that we've learned. So how does a course like this look like? Well, it doesn't exist yet, but something like it exists. So I have been teaching for the last, not this past year I've been away from teaching, but prior to that, for 2 years, I had been teaching a course called Better Living Through Data Science. And two things I want to mention here is that this was a first-year seminar, so students take this course in the first semester of the first year of their undergrad. And these are students who have already expressed interest in wanting to be in a quantitative field. So I've gotten a chance to work with a small group of students over the last couple of years to develop this course, and the goal is to scale this up for a wider audience in the university. The curriculum is such that we start by data gathering, then we do some data wrangling, exploratory data analysis and visualization, then we jump right into multivariate modeling. So we need tools that would allow us to do that. We talk a little bit about basic inference, both from a frequentist perspective and from a Bayesian perspective. And finally, communication is inherent throughout the entire syllabus. The course works in both individual work and teamwork. We have in-class exercises and projects that students work on in teams, and the in-class exercises are essential for that thinking together aspect. And we also have individual accountability through homeworks, a take-home, midterm, and a final. The assessment is such that we don't just assess the final work, but also the entire process. We have both peer evaluations and also contribution diagnostics. Students actually submit all of their work through GitHub repos, and myself and the TAs associated with the course are giving feedback there. So everything is documented, not just at the final stage, but also throughout the process as well. In terms of the assessments, we have some culminating assessment. That's a final open-ended project on data of their own choosing, and that's a team-based project. Also, every single class, there's a semi-open-ended application exercise. I'm calling this a semi-open-ended application exercise because it is open-ended, because we don't want every team to be basically getting to the same answer. But at the same time, there is some direction because there's limited time in the class where this discussion needs to happen. The associated code needs to be implemented, results need to be figured out, maybe a visualization needs to be made, and a story needs to be told. That's a lot to do in 75 minutes, in addition to some instruction from the instructor as well. So we try to keep those narrower in context. We also have periodic semi-open-ended homework assignments that students do individually, and these get graded by myself and the TAs we grab their work on GitHub, we rebuild the whole repo, and then give them some feedback. That takes time. So one thing that I've realized in the past, that the first time I ran this course that was missing, is something that is individual and has fast feedback. So the first thing I did was, oh my God, I'm horrible. So we have a learning management system called Sakai, and you can build in quizzes to that. So I went through painstakingly coding up questions in there. I wish that upon nobody. It was very good for fast feedback, though. And what that means is you can teach some syntax in terms of R syntax or a statistical concept in class and tell students, 20 minutes tonight, do this. And the next time they come to class, they still remember at least more pieces of it than if they had not done that quick feedback exercise. So I think that the need is there, but the tool was not the right one. I've also tried assigning some data camp courses to students, which worked well, though they're slightly longer, so then we were kind of chopping them up. I've used things like Code Academy, TryR, whatnot. The one thing that was missing there is that it was difficult to make it exactly tailored to what I was doing in class. So the next thing that I'm going to talk about is a new package that I haven't been involved in the development of, but I'm very excited to use it, called useR. So the package is on CRAN if you would like to take a look. And there's a whole website for it that has kind of examples in terms of what the results, what you can build, these tutorials that you can build with it. So here's one example, and actually these were developed by Garrett Grolleman from RStudio, so I just took a few screenshots of that to exemplify. You can have some narrative and also visualizations to go along with it, and students can actually interact, run code that are in chunks, and submit their answers. And if you want to kind of give them a success message, you can give that there. That tends to be encouraging, also informative. You can also code in some multiple choice exercises there. And the reason why I'm really excited about integrating something like this into the course is I think open-ended projects are fantastic, and I think longer homework is really what really makes students sit down and think about what they're learning. But if you have a course scheduled Tuesdays and Thursdays, there's only so much you can expect from students in those days. But you need to keep them busy with something so they don't forget what they learned that first day. And I think these fast feedback exercises work really well for that. And with the useR package, I'm going to be able to do that very tailored to the class that I'm teaching so that I don't have to give them additional information as do this, but not that. This is the content that's related to our class. This is not. So let's talk a little bit about the computational aspect in the course. And I'm going to do this in 3 pieces. I want to talk about the core setup. We use R, obviously. That's why I'm here. And we do students interface with R through the RStudio server. In terms of the toolkit, it's mostly tidyverse. There's some other stuff there as well. And reproducibility is a core component of the computation, and we achieve that using R Markdown and also Git and GitHub. So, why this setup? Here's my pitch for it. This would be the instructions that I would give my students if we needed them to install things locally on their computer. Now, all of you are experienced R users, so I need you to close your eyes and think back to the first time you were learning R, or perhaps even further back, the first time you were learning any computing language. And say you go to class and now you're given these instructions. You have to go to this website and install R. Well, if you go to that website, you need to, if you can picture how that website looks like, you need to figure out which operating system you have to go there, you need to think about versions, what do versions mean, I don't really know. Then you go to the RStudio website, what does an IDE mean, I don't really know. What does a package mean, I don't really know. And what does it mean to install the package versus load the package? So obviously, as the instructor, you might think, it's my job to tell them these things, and it very well is, but it takes a while, and we want to get to the punchline as quickly as possible. So I prefer giving these instructions to my students. Go to this address and log in with the same information you use to access your grades. That is the only login students don't forget. And there you go. We're in an RStudio window. Nobody had to talk about what a package is, what IDE is. And in fact, I can preload an R Markdown document that they can knit on the fly, and we can make our first visualization. So the goal is to minimize the onboarding friction and time to first data visualization. I give myself generally the goal of, at minute 10, are we looking at a picture that's worthwhile to tell a story about? And with this setup, it's pretty easy to do so. We want to avoid the local installation, so we have been using RStudio Server Pro, which kindly RStudio makes available freely for academic usage. And at the end, we provide instructions for help with local install. So if you are thinking, okay, this is great, but shouldn't an R user know what a package is? Shouldn't they know how to install things? And you're very right. I just don't think day one of class is the right time to communicate that. So indeed, actually, what I like doing is telling my students towards the end of the semester, setting aside some time in class or in office hours and say, hey, if you want to come and let's get all of these things installed on your computer locally, I will be there with you to make sure everything is running. It also saves me a lot of sanity of debugging installation problems on various operating systems, potentially in different languages. So I think this is a happy medium for everybody involved. In terms of the toolkit, we mostly use the tidyverse, and here is my why for it. One of the things that students like doing, especially at the end when they bring their own data set to class, is the data comes in some way and variables need to be recoded, okay? People love still coding variables numerically. 1, 2, 3 means low, medium, high socioeconomic status, for example. But nobody wants to see those numbers 1, 2, 3 in their plots, right? So we need to learn how to recode variables. Well, this is one way you might do it in useR. There are a variety of ways. This is one way you might do it. It's actually a pretty concise way. And this is one way you might do the same thing in the tidyverse. And in fact, I'd say here the useR solution is more concise. So if that was the only goal, I would potentially go with that. But what if I have a variable that actually, instead of 2 levels, has 3 levels? The extension in the tidyverse solution is only 1 line of code, right? Everything else stayed the same. Versus with the same construct that I had used in useR, now I have nested if-else statements. If the number of levels grow, this gets to be a little bit problematic. So I'd rather teach my students a method that they can extend easily without me having to foresee what types of data they might bring in when it's time for them to bring their own data set. Here's another comparison. Visualizing multiple variables. As I said, one of the goals, and this is a goal that is not just my personal goal. If you're familiar with the guidelines for teaching undergraduate statistics that the American Statistical Association puts together, one of the key components of it is multivariate thinking. So we want our students to be able to visualize multiple variables at once. Here is a plot that you can make using useR, where you have 3 variables being, information from 3 variables being conveyed. Again, this is one way that you can do it, but you're going to need something around this, right? We need to indicate some sort of color somewhere, and we're going to need some sort of legend to convey that information. This is what it would take in the tidyverse. The legend is placed automatically for them. The student doesn't need to know, is it automatic or manual? That's the first level versus the second level. They don't need to kind of think about, where do I place the legend? This is an awful placement for a legend, for example, so they'd need to tweak that a little bit. So we can kind of get rid of all of that. And again, the goal here is extensibility. What about one more variable? What if I now want to facet by one more variable? In useR, now I'm going to need to split my plotting space, potentially split my data set into subsets, and then plot them separately, versus in the tidyverse, all that's going to take is one more additional line of code. So yes, I would need to teach them something new, but it seems to follow what they've already learned, as opposed to a whole new construct of taking subsets of data or splitting your plotting space. So the idea that I want to convey here is not that one should do all their analysis using the tidyverse tools. I think one should choose whatever works for them once they get to the maturity that they feel like they can choose. But if you have limited time to teach people these concepts, think about which toolkit is going to give you the most consistent syntax across the different goalposts you have in terms of your learning objectives. Because the less friction we can get there, the more content we can actually get through. So the tools that are available within the tidyverse, they're closer to human readable most of the time, and I think that's what makes them attractive. The consistency of syntax is also an attractive component. And most importantly, for the type of course that I am talking about, introducing students to working and doing exciting things with data, the ease of multivariate visualizations makes it very attractive. So with that server setup and a few lines of ggplot2 code, we can actually get to that faceted graph in about 10 minutes. And I think that that's a fantastic improvement from having to go through all the stages of install and thinking about vectors and subsets and plotting spaces and splitting them, so on and so forth. Lastly, in terms of the computation, I'd like to talk a little bit about reproducibility. So here's a toolkit that we work with, but maybe let's talk about why we use this toolkit. So in terms of writing up their analysis, and not just writing up as in text, but also completing their analysis, everything happens in an R Markdown document. What this does is that it trains new analysts whose only workflow is a reproducible one. So if your students never do run code in the console, you don't have to teach them to not do that, or to, whenever they do that, to make sure they save it in some R script or an R Markdown file, so on and so forth. So you have to think about this as people, not people changing their habits to be more reproducible, but people having absolutely no experience doing anything in R and only learning to do things a certain way. And will 10 years from now, will there be something shinier and cooler and better? I hope so. You know, I'm sure there will be. But I think it's important to teach them the state of the art at the time. In terms of the pedagogy, doing their work in R Markdown is really helpful because it puts the code, the output, and the prose together, as opposed to having to run your analysis in an R session and then copying and pasting results into another document, say a Word document or a Google Doc, because that definitely breaks the paradigm of your analysis being iterative, and in fact introduces a lot of room for error. Prior to using these tools, I would indeed teach students, do things here, and then when you're happy with the results, make sure you copy them over to your document for submission. And more than half the time we were dealing with things like, oh, I'm sorry, I didn't mean to submit that one. I actually had this other plot, I just forgot to copy and paste it. So we want to get rid of all of that. Another thing that I think is really nicely built in, that honestly has nothing to do with reproducibility, it's just a nice bonus, is the syntax highlighting that comes in R Markdown. So when students compile the document, the syntax that they see is highlighted. If you've ever looked at code in Times New Roman font in a Word document, I think you know what I mean by you never want to do that to yourself. But if your students are turning in their work in a Word document, it's inevitably going to happen. With this paradigm, the code is highlighted, which means functions are always the same color. Strings are always the same color. Argument markers are always the same color. And some of us, not all of us, but some of us, in fact, do learn better by color coding. If you were one of the people who had many highlighters in high school as opposed to just the yellow, you know what I mean. So let's give the opportunity for students who do learn from these visual cues to actually get them as easily as possible. Notebooks is another cool feature of R Markdown. I do know that some of my students kind of have this idea that I will knit my document when I'm ready to do so, when everything is all well and good. They're rarely doing things at this level that are computationally so expensive that they can't just knit all the time. It wouldn't take a whole lot of time, but it's still nice to feel like I'm just going to do this quickly on the side. And just going to do this quickly on the side with the notebook functionality means you're just going to hit that green button on your R chunk, as opposed to carrying that over to your console, making sure everything is loaded properly in the console, so on and so forth. So these two things down here, nothing to do with reproducibility, but nice bits that make the experience a bit more pleasant for students. It's also efficient. And here, this is not so much about perhaps the students, but my TAs liking me. So people who have to grade data analysis work really appreciate it when formatting of the documents that you receive from your students are very similar. That consistent formatting actually makes it a lot more efficient to scan through things a lot quicker. And the thing is, the show your work part, which is something we always have to tell students over and over again, and they still fail to do it, is built in. There is no way to generate a picture in your Markdown document if you don't have the code that's required to generate it. Maybe there's a way. Maybe you can like embed a PNG in there, but well, they don't know how to do that, so. Sure, there is no reasonable way to do it, and I think that's what makes it nice. They can't not show their work. That makes it good for grading, but also that makes it really helpful for them because they always know what was the code that produced that exact plot or that exact output. In terms of keys to success with doing this, because I think this idea of teaching R, computing for the first time, and then adding a layer with a little bit of Markdown syntax, it's a light syntax, but it's something new, one other thing they need to learn. I think it may not seem as natural to everybody, but I think that with iterative development and knitting early and often, this is what I always tell my students, you wrote a piece of code, knit it, see what that does, and now let's move on to the next thing. What that does is, if the document compiles, students know that if next time there's an error, it was not that little chunk of code that did it. Yes, there's cursors over there that will tell you which line to look at and whatnot, but especially when we're talking about novices, I think reading errors is not the first thing they do. Generally, the first thing they do is to throw their hands up in the air and say, it didn't work. You did it, it worked, it won't work on my computer. So this idea of if you knit early and often and see the compiled document and then add a bit more and then add a bit more, it makes the onboarding easier, and it's actually a lot closer to how real data analysts work, which is in an iterative fashion. We don't just sit down and write up an entire data analysis. We do a little bit, we look at the results, we think about it, we decide, do I need to track back or can I keep going? Another component of the reproducibility aspect, which also feeds into the collaboration, is everything happens on GitHub. So we don't actually use a learning management system for the course anymore. I only use it for like reporting grades type of thing. But all the submission happens here. So with Git comes version control. And I think this is really important for anybody, but especially for a group of new learners. There's going to be lots of mistakes along the way. And the ability to keep track of it and to be able to revert back is essential. It's especially essential if people are working in groups and the members of the group might have different experiences, which potentially makes them overwrite something a friend had done at 2 in the morning and then the next morning realize, that one's not the right thing to do. It's a great platform for collaboration, and we actually encourage the students to use that interface, and they do. So within each of the repositories that they have, each assessment gets a repository, so a homework, project, whatever. They open issues, they tag each other, they say, this is your turn now. They tag us in terms of the teaching team of the class. We give them feedback. So we actually use all of this. And sure, we could be doing email as well, but then it wouldn't be so tightly connected to the work. And it's that close connection to the work and constantly looking at the code that you're writing that gets them a lot more time thinking about that, as opposed to having to constantly change platforms to communicate with the instructor versus do data analysis. It's also great for accountability. At the end of an assessment, I can go in and look at how many commits each of the team members had done. Now, number of commits is not a great measure of contribution because, commits could be a variety of scales, but a 0 is meaningful, or a 1 or 2 is meaningful if all the other team members have 20 to 25 commits. So it's great for accountability as well. Finally, it is an early introduction to tools that we all are using. And I think that because mastery takes time, the earlier we introduce the students to those tools, the more they're going to have an opportunity to get better at them. I don't think anyone in their right mind would claim that Git felt like very natural from day one to them. I think we've all ran into issues. I still, when students have problems with it and come into my office, we sit down with them, we Google some stuff on Stack Overflow, we run the code, I cross my fingers and say, I think this is going to do it. We hope we don't burn the entire repository down. So it takes time. And if they've started early, they're going to have more time for it. Additionally, it gives them marketability and discoverability. So the GitHub repositories that they work in are private to begin with. That's actually for a variety of reasons, one of which is legal. By the FERPA Act, we cannot actually publicly disclose the names of students that are enrolled in a particular class. I also do not think it is right for an instructor to have to make their students have to put their work publicly out there if they're not yet ready to do so. And I think some of their early work they may not want to be discoverable by potential employers. But at the end of the semester, I talked to them a little bit about, here are some assessments that if you would like to turn to make those repositories public, you're allowed to do so. These tend to be things I'm not planning on repeating, things where they had brought more of themselves in than small homework assignments. And it builds them a profile. So now what we're talking about are first-year undergraduates who are looking for internships at the end of their first year at school, who have a GitHub repo with a few projects done in R. And I think that that's a great place to be as a first-year undergrad. And I have had, this is anecdotal, but I have had a handful of students who have told me that this indeed came up when they went to their first internship interview. All right, so let's move on to the content. So we've talked about kind of the infrastructure. Let's move on to the content. I've selected 3 examples from the class that I'm going to walk through. And as I said, I'll be showing my students' code to go along with that and the results that they have achieved. The first one, the data set is actually a data set of paintings from Paris auctions. So I'm going to take a detour for a second and talk to you guys about a program we have at Duke that I take no credit for, except I've been a great benefactor of it. It's called Data Expeditions. And basically the idea is that the goal is to design an element of an undergraduate course that introduces students to exploratory data analysis. And what it is pairs of graduate students work with the course instructor to formulate a question or pathway. And these graduate students who take the time to do that are awarded a pocket of money as a travel grant. So the university has set aside some funds. If I remember correctly, it's like $1,500 for the 2 of them, times, I don't know, 3 or 4 that they award a year. So the students bring in their data to the class. They also help the instructor create assignments and assessments out of them, interact with the students in terms of talking about their data, and then help with kind of working with the students in terms of office hours and grading and whatnot. The lovely students that I had the privilege to work with are Sandra Van Ginhoven and Hilary Koch-Kronheim. These are both PhD students in art history. And what they did is an incredible task. So this is an auction catalog from the 1700s from Paris. Hilary and Sandra both talk French very fluently. My accent isn't so good, so I'm not going to try to read to you what's happening there. But that auction catalog basically describes this particular painting. And here's the English presentation of it. So in the catalog, there are things like 2 paintings. Here is 17 inches and 3 lines high and 23 inches wide. It's painted on wood, so we know the material it's painted on, and then some description of what's happening in the painting. So these are all written by the auctioneers, and oftentimes when people were bidding on the paintings, they didn't initially get to see the painting themselves, but only looked at the auction catalog. So Hilary and Sandra wanted to see how does the description in the catalog seem to be related to what price the painting goes for? Or are there particular features of the painting that's related with higher final auction price? So what they did is for 3,000 or so paintings, they went through the auction catalogs and actually digitized the data by typing it into Excel, actually. So the highlighted row, so imagine this is like a really wide Excel table. This is coming up. Do I know what I'm doing to do this? Okay, give me 1 second. Can you hear me? Yes? Okay, great. So this is one wide Excel table, and the highlighted row is the painting that we were looking at. So for example, you can see that 17 inches tall and 23 inches wide record there, okay? So they actually came to class and described to the students exactly how this process went. So the students were able to see from the data collection how the data came about. Also, something students love doing in stats classes, and when things don't work out, they love saying, we need a larger sample. Well, you don't get one. This is it, okay? This is all the auction records we had. So this idea of needing a larger sample seems like a great solution to a lot of statistical problems, but sometimes it's simply not feasible. And I think it's good for students to see this in this situation. So the paintings are from 1764 to 1780. We had 3,393 records. I just want you guys to remember that number. And 57 variables. So that's a big data set for students to be starting off with. Initially, we needed to do a bunch of data cleaning because, well, things were kind of noted in many funny ways in the Excel file. Is it okay? Okay, thank you. I feel very pop star. And clearly it doesn't work on me. Not a good fit. Okay, so we start a little bit with data cleaning and wrangling. Then we do a bunch of data visualization. And the goal is to explore patterns and possible interactions. So these two PhD students that came to us, that worked with this program and then came to me, the reason why they did so is because if the question they were asking could be easily answered with one linear regression, they probably could have figured that out themselves, okay? But they needed to do a bit more, and that was out of their expertise. So it was a great experience for them to get something out of these students who know statistics, and for us to get something out of them, which is this data set that only they own, and our students were the first ones in the world to work with it. And we did a bunch of modeling. So the prices, as you can imagine, were very right skewed, so we decided to do log them, and things were looking a lot better that way. So we were doing some procedural and expert opinion-based model selection. And we had the experts in the room with us, so students could actually ask them questions like, does it even make sense to interact these two variables? Would the interpretation make sense at all? So that was a great experience of both learning the tools and also thinking about, what does the data say? What are the people who have a vested interest in this data set actually want to find out? So I had not taught them any sort of similarity matrices or anything like that, but one of the teams decided to come up with this, and their final result was that Spanish art apparently is most notably different from the other schools, like Dutch, Flemish, French, German, and Italian. And they presented this, and we could see Hillary and Sandra going, yeah, actually that absolutely makes sense, and that's a fantastic thing for students to see. Another one here is, and again, maybe one would make different stylistic choices in terms of the plots themselves, but what they were able to find out here is that the colors are a bit funny here, but the C here, the green line, stands for copper, where the material is copper. And you can see that the green line is a lot steeper than the other ones, and the surface area only goes up so far. It turns out that copper paintings tend to be a lot smaller, and as the surface area increases, the price goes up a lot. Is it the content of the painting? It seems a bit more like it might actually be the material that's driving up the price. So that was something that wouldn't have been possible for the researchers to uncover if we weren't looking at these multivariate visualizations. In terms of the experience from the students, they were interested that this was a non-standard application, something different than what they're used to seeing in many of their stats classes. And they said that the unfamiliar variables made the narrative very challenging because there were variables that were a lot about the content of the paintings, that if you had some background in art history, they might be meaningful to you, but if not, not necessarily. They said massive data. 3,300 rows, so massive data was overwhelming, but expert opinion made it refreshing. And it is indeed a massive data set for them, because my guess is the previous data set they may have worked with in high school had 30 observations. And it was a novel application, so they didn't have any preconceived notions coming in that pushed them for further creativity. Here's another example. For those of you who are not from the US, for many Americans, the university that I'm in, the name Duke, does not mean a university, but it means a basketball team. And our students are very, very interested in basketball, and it is often very challenging for faculty to deal with this fact, because they camp out for months outside to go to basketball games and get sick and don't come to class. I decided to take the if you can't beat them, join them approach, and said, fine, then we'll do basketball in class. So here's the website that I think it's a subsidiary of the sports group at Duke, that they put all the basketball stats online. And we told the students, how would you get these data in so that you can do something with them? They said, well, I would copy everything and paste it into Excel. And then I guess you spend the rest of your life kind of undoing these links and stuff like that, which is just no. So here's what we can do. Using the Arvis package, we can scrape that data, and this is exactly how many lines of code it takes. So to go through this, I do need to teach you. If you've ever used this package, there's an add-on that you can use called a selector gadget, so it tells you where on the website what the tags for certain elements in the tables are. So going through this, teaching this, maybe takes about 15, 20 minutes of explaining what's happening. This comes a little bit later in the course, so they know what the pipe operator is and whatnot. And voila, they can get to this answer. They have it in Excel. Maybe we do more with it in terms of string parsing. Maybe we don't, depending on what their learning goals is. And now they can visualize the data. And now they have a tool that they can scrape data with. So for that final visualization, they actually can go and get their own data if it's not already in a data set format. And that's very empowering for them. Well, best laid plans. So I assigned this one year right before Thanksgiving, and the website went down. And over Thanksgiving, you can't find anybody on campus to try to fix anything. So what had to happen is that I had to extend the deadline for it. So the thing is, if you're going to be working with real data, you're going to have your students interface with something like this, you got to be open to unexpected surprises like this, and you need to be able to adjust, or download a local copy of the website, put it on your server, and then you're good to go. Lastly, I want to talk about teaching interactive visualization tools. This is sometimes what students look like, and then you go like this, and then this is what they look like. Okay? They love Shiny. Because it gives them a tool to move from doing data analysis to what looks like something else. Something more, but the nice thing is they don't have to learn a whole new language to do that. So I teach Shiny for about 2 classes of the semester. Out of about the 28 sessions we have, only 2 classes towards the end to give them a taste of it. And just about every group ends up putting in an interactive data visualization in their final project. I have to admit, sometimes they're not necessary. Sometimes they're not necessarily showing something all that interesting. But it makes the students want to learn more. And I think one of the goals of a course at this level is that they come back for the second class. And it certainly helps with that, and I think that's a very impactful thing. So here, one of the groups had gotten some data from an open data website on Durham or in North Carolina and looked at fatal car crashes. And what they did here is I do not teach them the ggmap package at all. So it means by the end of the semester, they know enough to be able to read some documentation on a new package, or at least crib stuff from Stack Overflow to come up with the map, embed it in a Shiny application, and have something interactive where they're able to do a multivariate visualization, latitude, longitude, type of crash. And that's a great place for students to be at the end of their first semester in an undergraduate class. So in terms of the interest and impact, as I said, the students I've worked with so far were part of this program at Duke that happens in the first semester of their undergraduate career. I have asked the program coordinators what does the interest look like for this particular cluster as opposed to all the other clusters that exist in this program. So students, in addition, instead of quantitative cluster, could choose to be in a humanities cluster, a social sciences cluster, so on and so forth. They said they don't have hard data. I mean, they clearly do, but they didn't share it with me. But they said definitely a significant increase in applications the last 2 years than previous years, which was when the data science class was added to the quantitative cluster. In terms of students that go through this class and then who said that they are interested in doing more in terms of data science and statistics. The 2 years that I have this data, 76 and 83% of students have expressed interest in that. In terms of pipeline into the major, the first year that we taught the class, 19% of the students declared the stats major. The second year, 31% of the students, and the third year, about 40% of the students have either declared or expressed interest in continuing on with stats. So that's a great pipeline for us. That means that many students coming in with the necessary R skills that we can take out of the introduction bits, we can take out of a more advanced class and put other stuff there. In terms of diversity, here are the percentages for the percentage female in the class. In our probability theory class, which used to be our existing pipeline into the stats major, that number is rarely above 25%. So we're definitely seeing higher numbers here. And in terms of curricular considerations, this coming year in the fall semester, I'm going to teach the small class as I've done before, and in the spring, I'm actually going to be offering the class as a gateway to the major that's open to all university students, and hopefully we'll be able to scale things up, but still keep the content there. Thinking about this as a starting of the curriculum, I think there are 3 points that I want to make. I think we need to move away from ad hoc computing education or expecting students to pick it up along the way. I think this is true for undergraduate education. We actually see this a lot in graduate education as well, especially in, let's say, I've been through a statistics PhD, real analysis or large number theory, these were important classes, and they are. But nobody took the time to teach computing. That was something that was assumed you could pick up along the way. And I think that that is not the right way to go, because people will pick things up, but you are not guaranteed that they're going to be picking up the best practices. And I think taking the time to impart this to the students as part of your curriculum is hugely important. Uniformity of tools is really important as well. We would not be able to get through as much as we do if I kept changing paradigms in terms of coding every other day. We need to keep things consistent and think about it as what are the tools they're going to need at the end, and how can I partition it to the different classes I have throughout. So choose a toolkit that works for you and stick with it. Or think about what really complements it. So don't choose the package that first comes up as a solution. Think about how would teaching this syntax go versus something else, and how does it fit into the bigger picture. And lastly, teach computing early without any prereqs. You can teach this stuff without a calculus prerequisite or a probability prerequisite. So take advantage of that. So teach it early and teach it often. Thank you very much. My slides will be posted after the talk.
Okay. Very good. We have a couple of minutes for questions. If anybody would like to ask Mina a question or make a comment. Yeah. Do we have anybody that can go with a microphone, or perhaps you can come forward? Not too far to come. Thank you.
I'm Spencer Graves. I'm one of the three organizers, number three of the organizers of the following plenary, and I want to invite all of you to, especially our speaker here, to come and give us your ideas on how to make R easier for everybody. We've got three parts, but you know, we can talk about that later in 20 minutes after your break.
Great.
Okay, thank you. Any other questions or comments? Oh, we've got a couple at the front. I think I can walk down. Let's see. Hopefully it won't make horrible noises.
You mentioned grabbing some code from Stack Overflow. How do you deal with plagiarism?
So that's a really good question. How do we deal with plagiarism? There are a few ways that we deal with it. So in terms of plagiarism between students, the way the GitHub repositories are set up is I have a GitHub organization for the class, and there is a private repository for each assignment per team or per student, depending on whether it's a team or a student. And myself and the TAs get access to all, but they can't snoop into each other's repositories. If at any point we're doing peer review, that gets opened after the submission deadline. In terms of if we were to say plagiarism off the web, for example, what I tell them is that they are welcome to grab stuff, but they need to note it, and they need to know where it comes from. And I realize that even if they don't note it, there's not necessarily a way that I will always catch it, but I think realistically speaking, if somebody told me I have to do something without looking at answers online, I'd feel a little bit paralyzed. I think any of us who have to do work without internet know that. So I don't need them to be these superhumans. I need them to have the tool, like the skills that we all want people to have. But I do ask them to note it so that they get into the habit of crediting people whose work they're grabbing from.
Another question over here. Yep.
I was wondering if you have any guidelines as to how to grade data science projects.
How to grade data science projects? So yes, so I guess we end up doing a whole lot of that. There are a few things that I think about in terms of, so let's think about like an open-ended project as opposed to a homework where a question where there was one right answer anyway. One of the things that I have actually veered away from using is the word interesting data, because I think what's interesting to one student may not at all be interesting to me. So I used to find myself saying, find an interesting question to answer, and then we get very frustrated that this is not interesting at all, but maybe it was for them. So I try to think about part of the points go into them describing why it's interesting to them, why they think that's an important question to answer. And important doesn't mean it's important for humanity. It could be important for them. Then we think about the analysis, and in terms of the analysis, we think about two things: statistical correctness and also the syntax. Are they really using best practices in terms of the syntax, or are they doing other stuff? And if they're doing other stuff, you know, even though I teach a particular suite of packages, in terms of the work that they do, they don't have to use them. But if they're choosing to go outside of that, they need to explain why they did that. And if they're if they're making mistakes, then they get penalized for that as well. And then part of the points go into the narrative itself. A lot of students do things like, I'm going to do table, 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 plot, 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 and then one paragraph at the bottom. And I'm supposed to read that paragraph and keep scrolling up and down to see what that means. So we try to teach them that is not how an analysis should look. Your narrative should be closely followed by the results that that narrative is based on. So the points are split in between those. And I am a big believer in writing rubrics. It was mentioned that I teach a course on Coursera. Part of that means strangers grade your work according to a rubric. I have gotten a lot of experience of writing very detailed rubrics. If you are teaching at scale, I think that's a very important thing to invest time in, as excruciating as it can be, and assigning points to certain things that you want, and then leaving some bonus points for extra flair.
Okay, thanks very much. I think we have to leave it there, but of course, Mina will be around for the rest of the conference, I think, and so please, feel free to approach her and discuss more. Can we thank her? Thank you.
Thank you.